Okay, today is another double header lecture. And today's material that we're covering, I think maybe for both parts of the lecture, but certainly for the first part, is not covered in our textbook, the Barton and Sutto, or Bartow and Sutton book. And so here I've mentioned several readings that I think are very good for the material that we're covering today. And so I urge you to read those if you want to really understand this material. By the way, all of these are accessible if you're on the CMU network. So we have library permission to all these. So you shouldn't have any trouble finding and downloading these. Okay, so we're going to talk about policy gradient again today. And just to swap us all in, remember the policy gradient theorem. That was the key, it's up there at the top of the screen, to allowing us to figure out how we could use gradient ascent to optimize our objective for reinforcement learning, which is J is our objective. And of course, that's one way to define it is that we want to maximize. We want a policy pi that gives actions that maximize the sum of discounted expected future rewards. We can also define J in terms of average reward or the episodic reward in the case of episodic trajectories. But this policy gradient theorem holds in all of those cases. Okay, so this is really the thing that tells us what is the derivative of that objective with respect to the parameters theta that define the policy. And I want to start by noticing that we can write this in several forms. For example, I can take that top thing, and this is just a review, we did this before. I can multiply by pi of theta and divide by pi of theta over here and not change anything. But then if I do that, now I can write this noticing that the first terms up to here are really just a way of saying we want the expected value of this quantity to the right taken over the distribution of states and the distribution of actions that will be generated by the policy pi theta. Right? So then for simple thinking and for simple notation, we can simply write this as the expected value over pi theta, that's all this, of this quantity. And then as we noticed before, this quantity is simply equal to the gradient of the log. So this will be actually the form that you'll see mostly in the lecture today. And I like this way of thinking about it because then you can say, well, it's the expectation over the state and action distribution generated by pi of that. Okay, so given that, we've talked about actor-critic models before. One way to define actor-critic algorithms is that they maintain two different sets of parameters. You learn two different functions. One is what we'll call the critic, which is an action value parameters. For example, we might learn an estimate using parameters W for the Q function. And then the actor is the policy itself, which has its own parameters, theta. And we've talked about algorithms for actor-critic and using them both to update, to learn a good policy and to learn the corresponding Q function. And a typical way to do this is to update the policy by using our approximation to Q. That would be one way to do it. Then it's only approximately correct because, of course, any function approximation that we use could be wrong. And the actual policy gradient rule requires that this be really Q of pi, not some guess about what Q of pi is. So this would be an approximation to the gradient. And if we follow that, then it leads to the update rule. Notice the upside down triangle is the gradient symbol. The correct side up triangle just means how much we're going to change our parameter vector theta on each gradient ascent. And so if we follow this gradient, it leads to an update to theta, which is some learning rate times just that gradient. Okay, this is all review. And we've also talked about reducing the variance in estimating these things, for example, by noticing that we could add in a baseline to our quantity without really changing the gradient. And so we mentioned that a good baseline to use is the value function itself. And that allowed us to define what we call the advantage function. The advantage function for some policy is just the difference between the Q value and the value of being at the state. And so you can think of this as the advantage of taking action A from state S. Okay, and so given that we can think of this as exactly one of those possible baseline B of S functions, then we see that we can actually rewrite our policy theorem. Instead of writing it this way, we can write it using the advantage function itself. Right? Because it's just totally equivalent to saying, well, we're treating this value function as a baseline, B of S. And we knew that we could add in any baseline. And again, the point of doing that was to reduce the variance in the training sample that we're going to get, because these advantage numbers will be much smaller than the actual values. And they will vary less. Okay, so again, that's kind of review. So today we're going to look at it really two questions. One is, the key question is, given that we're going to use function approximation, what kind of guarantees, if any, can we even provide, and under what conditions? The good news, there are some guarantees, but it does require very specific conditions, and we'll see what those are. The second thing we're going to look at is something called the natural gradient, which is a form of the gradient which is independent of the particular parameterization that we use for pi. And we'll get to the details of both of these. So let's start by talking about estimating the advantage function. If we're going to do that, then you notice that our standard temporal difference error, which is just this expression here, is in fact a perfect signal for the advantage function. It is the value of the advantage. So we can see that delta pi theta, which is just the observed reward plus gamma times the value of the downstream state minus the value of the upstream state, is a good estimate of the advantage function because its expected value breaks down to only not depending on the upstream state, but only depending on, if you think about what is this expected value taken over, what's the non-determinism here? It's the actual reward, which might be that we experience, which might be non-deterministic, and the outcome of taking an action, which might be non-deterministic. And so the expected value of this quantity is really the expected value of the observed reward plus gamma times the value of whatever state we actually end up in. But this is effectively a constant that's not influenced by that non-determinism. And then we do know that the expected value of this is the definition of our Q function. And so you can see that this is actually the expected value of this quantity as we sample it is exactly the value of the advantage. And so if we want to, it turns out if we want to train a function approximator to approximate some function, like in this case the advantage function, it's very good if we can prove, as we do here, that the sample of training examples we're going to collect is an unbiased sample in the sense that the expected value of that is the correct value for the function. Of course, it might vary, the sample of data might vary from sample to sample depending on the particular non-deterministic reward or particular non-deterministic transition that we end up making, but its expected value is what counts, because what we're going to do is, in all these sampling algorithms, the key is to find some quantity that we can sample such that we can characterize its expected value. Okay, so this is just a simple proof that this quantity here is a good unbiased estimate of the advantage function. If we keep sampling it, it'll be a good set of training data in expectation. Okay, and so this leads to another way to rewrite our policy gradient theorem. Remember here we originally put Q of SA. Then we, in the previous slide, replaced that with the advantage function of SA. And in fact, we can just use this sampled quantity delta, whose expected value is A. And again, since what we really need to prove is that the expectation of this over the state and action distribution of pi is the objective, then by sampling this quantity, by taking steps in the world, for example, we can see that it'll be an unbiased sample for this. Okay, so that's the kind of line of reasoning that we're going to be reusing. Okay, so in practice, despite the fact that we know delta pi theta is that quantity, and its expected value is the advantage function. In practice, we often are learning some value function, and it's, again, not the same as v of pi theta. It's our estimate of it based on some parameters, say v. And so again, we end up often approximating this by, instead of using the true delta of pi theta, which is hard to know if we don't know the exact value functions. And so we often use some approximation to it based on our estimate of what the value function is. So the key today is to keep a distinction between the true value or Q function, which the agent usually doesn't really know, and the quantities that it can sample, which it can observe, and in what cases can it substitute one of those for the other and still succeed. Okay, so it turns out if you look at the literature, here's a paper from ICML recently, people use different ways of getting at these quantities. For example, one way is to learn two approximations. One is to learn a function approximation for the value function based on parameters v, which get learned, and to learn also an advantage function based on some other parameters w, which get learned, and then to calculate q as needed in this way. And other people do it other ways. You could sort of learn any two out of these three and have the third, and that leads to different kinds of algorithms. here's in fact the advantage actor-critic algorithm, which is one that we've looked at before under another name, but you can see what it's doing is, in this case, this is for episodic. And so what we do is we keep drawing in action, observing the next state and the reward. And if you think about this quantity, this is really our estimate of the advantage. This is our delta, based on a parameterized learned value function. And then given that delta, that temporal difference error estimate based on our approximate value function, we use that to update both the parameters W, which are going to refine our approximation to the value function, and the parameters theta, which define the policy itself. So this is an actor-critic algorithm in the sense that it's learning both the policy and the value function. And in this case, it's using that estimated temporal difference here. Okay, so what we've seen then, to summarize, is this. So we've seen that we can write that policy gradient. In the reinforced algorithm, we just sampled the total discounted future reward until we got to the end of the episode, called that GT. And we just saw just now that we could also substitute the Q function or just the advantage function by subtracting out the baseline value, or just using these observed temporal difference error deltas. And they all give us stochastic gradient ascent algorithms. So now the key question is, will things converge if we use function approximation, and if so, when and how? And the nice thing is that there is an answer to this. It turns out that, of course, in general, if we have some parameterized by W estimate of the Q function that's not right, then we can't really guarantee that this is going to converge. But it turns out if we choose this in a particular way, we can avoid introducing any bias. That is, we can make sure that our training data is unbiased in the sense that in expectation, it gives us the values we want. And in that case, we can still follow the exact policy gradient. So what are those conditions? Here they are. This is the whole story, although it'll take some time and slides to kind of figure out the consequences of this. So it turns out if we're trying to do, let's say we're trying to estimate a Q function, which is one of the forms that we can use to get the policy gradient too, then if the following two conditions are satisfied, things are going to work. The first condition looks a little weird. We're saying that the gradient with respect to parameters W of the Q function must be equal to the gradient with respect to a totally different set of parameters, theta, of the policy function. The first time I saw this, it blew my mind. I thought there had to be an error. So think about that. And the second thing is we're going to train the Q function to minimize the mean squared error. That is, the objective we use for our function approximator is minimizing the squared error. Now, if these two things hold, then we're able to show that the true policy gradient, which of course is this quantity, based on the true Q function, Q pi theta, and of course that Q function is not known to the learner, so it wishes it could use this, but it doesn't know Q theta. But it's going to turn out that under these two conditions, it suffices to use the estimated approximate Q function parameterized by W, and this policy gradient is exactly this. That is, the expectation of this quantity is the expected value of this quantity. Okay, now we'll prove this very easily. So one thing to notice is this. So there's my definition of error up in the corner, right corner, just copied over from the previous slide. We're saying the error we're trying to minimize is just the squared difference between the true Q function, Q pi, and our estimate, Q sub W. And so if we want to prove that this is this will give us an unbiased estimate, all we have to do is notice that when the function approximator converges to minimizing that squared error over its training data, then the gradient of that error with respect to the parameters will be 0, because of course that's what's going to happen at the maximum as we vary the parameters W. The slope will be 0 at the maximum. And so we can rewrite that error, the gradient of that error, by actually taking the gradient of that quantity up on the right. You see the gradient of that with respect to W will be 2 times that quantity times minus the gradient of QW with respect to W. Right? It's just freshman calculus. And so if I write it out, I get this second line. Right? It's just 2 times this quantity. Oh, what happened to the 2? Well, it equals 0, so I just multiply both sides by 1/2. So it equals this quantity times the gradient of that quantity, which only the second term, QW, depends on W. Okay, so now that I have that, from the other condition, I can substitute this quantity for the gradient of QW. Why? Because remember what we said was our first assumption was that the gradient of QW equals the gradient of the policy. So under that assumption, I can just substitute this quantity for the gradient of QW. And once I do that, I'm home free, because then if I just multiply this through, I get that Q theta times that gradient minus QW times that gradient, which I just shift to the other side of the equal sign, equals 0. And so those two quantities are equal. So that's a proof that instead of using this form for the policy gradient, we could use the equivalent, this form. Yep?
How do you ensure that the first condition holds?
This holds after the function approximator has converged.
No, I mean, how do you ensure that the Q function, the gradient of the Q function is the same as the gradient of the log of the...
Oh, yeah. We're going to have to come to that. That's what I say. It's not obvious how we arrange for that to be the case.
Okay.
So just stay with me for a minute, just kind of put that doubt aside. But if it is the case, and that was one of the requirements, then you can see if it is the case, then we can replace our tried and true, well-believed version of the gradient, policy gradient, by this quantity instead, using our approximation of Q. Okay, so we can just do that. Now here's a couple notes on this. Notice this proof did not require that the error be 0. It just required that the function approximator converge to the best error it can get. So maybe we have, let's say, like a linear function approximator that's not sophisticated enough, not complicated enough to represent the true Q function. That's okay. If you think about this, we didn't say anything except the starting assumption that it had converged, that the derivative is 0. Second, it turns out we only need this other condition to be true within a constant. And this will make life a little easier when we go to do things. And you can see it only has to be true within a constant, because suppose there's some constant c here that's some constant, and it's not on this side, so this is only true within a constant. Then you can see that the constant c will show up when I do this substitution. But again, just like the 2 that I multiplied through by 1 over 2, because there's a 0 over here, I can get rid of any constant. Yep?
So if the dimensionality of W and theta are different, then we only need them to be like within a matrix factor of different or something?
If they're different, then it's hard to arrange this condition to be true. Okay. So now let's look at this other assumption. How can we really achieve this? It sounds crazy. So first of all, it's going to require that the dimension of W, the parameters of Q, be the same as the dimension of theta. Otherwise, they won't be equal. Here's one way to achieve it. So suppose we're trying to learn a Q and a pi. Suppose we take our state action pair and we make up features. We engineer some features to describe that pair. And let's call that feature vector phi of SA. It might be like the pixels in the camera and the name of the action, for example, or any other kind of features you want to define. But let's say we have some feature vector that describes the pair SA. And then let's suppose that we decide to approximate Q as a linear function of that. That is, if this is a d-dimensional feature vector, we learn a d-dimensional weight vector, parameter vector W, to get a linear combination of those as our approximation to Q. And we do the same here. We take the same features and we learn a different linear function of those to be the log of the probability of taking action A given state S. Well, in that case, we made it true, right? Because now the gradient with respect to W of Q is just phi of SA. And similarly, the gradient of the log probability here with respect to theta is also phi of SA. So this is a way in which we can guarantee that this is true. And if you think about it, if I say y equals W times X, what's the gradient of y with respect to W? It's X. Right? So the gradient of Q with respect to W is just the input features. Well, this turns out to be very handy because if we combine this with, say, a deep neural network that, say, has some complicated state, and we use many layers in a deep network, and then at the end, we have some features that describe that input, then we can use those as our phi of S and learn both a Q function and a log probability function. Here, notice I went from phi of SA to phi of S, because here suppose, for example, there are three possible actions. Keep going straight, go left, go right, just to make it a discrete set of actions so that thinking about this is easy. In that case, this is some d-dimensional feature vector describing the input scene. And if I want, for example, for my three possible actions to learn a different weight vector, that's fine. And similarly, a different policy vector to assign a log probability to each, that's fine. And so now basically the Q function is, and the policy are both defined in terms of linear combinations of these features. And again, this will hold. Right? The gradient of this will be equal to the gradient of this because it's simply that. So now you see how cool this is. I think it's very cool because what it means is we can put in here any kind of neural net we want. And furthermore, we can train it to optimize, I guess, the minimum squared error for this and something for this, and get some features. And then, strictly speaking, given what we've said so far, freeze these features and learn the appropriate weights, in which case our proof will carry over. Question?
I was just saying that like it depended on either data or W, so I was wondering how you would actually train it. So could you explain more about how you minimize the squared error thing in the first phase of the training?
Oh, well, let's see. So what we said before was that if we minimize the sum of squared errors, and if this condition holds, then we proved that we could substitute for the policy gradient rule one that was using our approximation.
Yeah, I was just saying that doing the policy gradient will only optimize the theta that's multiplied against V. It wouldn't actually train the deep neural network.
Well, it would if we do back propagation. Right? If I train it, if I pick an objective here and an objective here, then I'll learn the W's, but I'll also have a derivative of that objective with respect to this quantity, which then in the standard back propagation way I can use to retrain the neural net.
So like training both Q and log of pi theta.
Right. Okay. Right. So this gets trained as a subset of this overall network. But if I look at this network in the right way, then I can see, oh yeah, this actually is exactly this situation where the derivative of this quantity, the gradient of this with respect to W, is the gradient of this with respect to theta. And in fact, there it is. So this is why it's so cool, because now we can, basically, it's not like we have to make up by hand these features. We can train a system in this where the overall objective is to learn one or the other of these, and still make this weird-looking situation true.
In practice, how much of a limitation is it that you're only doing like linear transformation with W and theta? Like, is the deep neural net constructing the features able to make up for that, or?
That's the right question, and the answer is roughly your mileage will vary depending on the problem. But it's certainly an argument for making, the state encoding of the input a very sophisticated function of the initial sensor data. Because that's a way, in fact, it's hard to think of forms of these two functions other than linear where you can make this the case. And so if that's what we're forced to do, then okay, let's make a very sophisticated. Yes?
So I'm curious about like the branch of policy gradient, like in traditional policy gradient neural network, there should be like a softmax layer at the end.
Say that again.
There should be a softmax layer at the end of the policy network to output the probability of each action. So in this kind of architecture, the output of the policy branch is the log probability of the problem.
Right. And so if you want to, so this is very compatible with using a softmax layer. Because you think about it, if what I can produce are the log probabilities for the different actions, then if I input those log probabilities to a softmax function, I will get out the probabilities.
So like, so for the previous like the update, parameter update for policy gradient is easily applied for this kind of architecture.
You can, yes. I mean, you know,
Is it exactly the same?
well, let's see. I mean, strictly speaking, the only thing remember the proof that we said that after the minimization of Q is achieved, then the gradient of Q with respect to W is 0. That was a key step in our proof. So strictly speaking, the only thing we've shown is that if we train this to optimize Q, if we train this entire neural network to optimize Q, and we get to a fixed point, we get to the optimum, the minimum possible squared error, then we can freeze all of these weights and train this using policy gradient where we substitute our approximation of Q. So strictly speaking, that's what we've proved so far. But in fact, a lot of these things converge in practice if you don't do it in that strictly staged way, but just let Q and the policy be jointly learned. Or as we talked about before, in practice, we'll often use the advantage function here. But you get the idea. So now you see how even though it looked crazy at the beginning, is not such a crazy condition as long as you do something pretty sophisticated to get your state or state action features and then just take linear combinations of those feature vectors for the functions. Okay, so this final idea I want to introduce today is the idea of a natural gradient. And I think we will say more about this as we get into more robotic kinds of applications. But the idea of a natural gradient is based on observing that the gradient we calculate depends on how we parameterize the policy. And it's well, for example, as it says here, if you even take something like a softmax policy and change the score for all the actions, you can change the gradient. Another example, which is in one of the readings that I suggested, compares polar coordinates with Euclidean XY coordinates and shows how those gradient with respect to those policies based on those two coordinate systems give different gradients. And the reason informally that this can happen is that if we have a vector of parameters, the gradients with respect to these different parameters are not necessarily really uncorrelated. They're actually correlations in the derivative of our objective with respect to these different parameters if we're unlucky. So the idea of a natural gradient is that we want a notion of gradient that's not dependent on what the actual parameters of the policy are. And we can define one in the following way. The natural policy gradient is parameterization independent. And it's defined this way. We'll say you can take the gradient with respect to the parameters that you have, but then you want to multiply it by a matrix, defined here, to get the parameterization independent direction. And what is this matrix? This matrix is called the Fisher information matrix. If you took 702, you know all about Fisher information. But let's look at this. What it is, well, here's a vector, which is the gradient of the policy with respect to pi, with respect to theta, and now we're just multiplying it by the same vector transposed. So then you tell me, what will be the ijth element of this matrix? So the ijth element will simply be the ith element, the jth element out of here, and the ith element out of here multiplied. So it's going to tell us, and if I take the expected value of this over the state action distribution given by pi, then what this is going to tell me is how correlated is the derivative of the policy gradient, of this gradient. How correlated is this the gradient of log pi with respect to feature or parameter I and the derivative with respect to parameter j. So it's basically going to give me a measure of how correlated those two derivatives are. And the natural gradient, if you want to know what the natural gradient is, think about this. What if we happen to have a parameterization theta where G is the identity matrix? In that case, the natural gradient will be equal to the gradient that we get from the current parameterization. So what that implies, right, in order for, if we happen to have a parameterization that gives us, by default, the natural gradient because G is identity, then what that means is that G is a diagonal matrix. And all of the off-diagonal elements are 0. So all of the derivatives of log pi with respect to parameter I and parameter j are uncorrelated. Those are all zeros in the G matrix. So this is the idea of a natural gradient. It's a way of saying, given the gradient that we have, we can transform it into something that's as close as possible, given that we're still using theta as our parameters, to a system where those individual derivatives in the gradient are uncorrelated over the distribution of states and actions entailed by pi. Seems like an okay thing to do, but does it really help? And the answer is it does really help. And in fact, it leads to a kind of surprising algorithm called the natural actor critic, which goes like this. Suppose we decide we're going to learn an advantage function instead of Q. And so we set up this problem. Then the natural policy gradient simplifies this way. Here's our original expression for the policy gradient, which we agreed we could use the advantage function instead of Q. But now, because we know the gradient of this with respect to its parameters W must equal the gradient of this with respect to pi if we're setting up our system to achieve those conditions, then this quantity itself is just its gradient times the parameter vector W. Okay, so this step from here to this is just using assumption 1, that the gradients of the A function and the log pi function are going to be equal gradients. And now once I've written it this way, you can see that this quantity is actually what I defined is the information, the Fisher information matrix. And so now I can target the gradient with respect to pi is just going to be the information, Fisher information matrix for theta times w, which are the parameters of the advantage function. And now if I want to transform this to the natural gradient, then as we said, what we do is we multiply that gradient by the inverse of the Fisher information matrix. And so if we do that, if I multiply this by the inverse of g, I just end up with this. Which again is kind of mind-blowing. But what it's saying is that we can update the actor parameters in the direction of the critic parameters. The critic in this case is the advantage function A. And that will give us the natural gradient if we, again, the theta parameter vector and the w parameter vector of the same dimension. And so what this is saying is we could use this as the vanilla gradient, but if we want the natural gradient, well, we can use this as the vanilla gradient. But if we want the natural gradient, what we should do is update our theta parameters using in the direction of the actor-critic parameters. And this is a consequence, again, of having this equality, which is the same as the equality of the gradient of A being the gradient of this. So we get a lot out of this shared linear dependence of pi and the value function on the same feature vector describing S and A. And this is one of the things we get out of that. Okay, does it help? Well, here's from the Peters and Schall paper that I recommend. Here's one where they applied normal gradient, shown in blue, and the natural gradient, shown in red, to the cart pole balancing problem, where the actions are basically to exert horizontal forces on the cart to try to keep the pole in balance. And you can see here the time in training minutes, and the vertical axis here is actually the sum of discounted future rewards, or the average reward. It's the policy objective. And so you can see that the red curve, which is using the natural gradient, is converging much more quickly to a good policy than the one using the vanilla standard gradient. Okay, so you do see that this can make actually a big difference. And this is particularly useful in situations where, for example, robotic actions are controlled by multiple joint angles, and so there could be a complex relationship between the parameterization of pi and, for example, the feedback that we're using, visual feedback using to describe what we're seeing. Okay, and there's another example from another paper, one of the other papers I recommend, that again shows faster learning curve. Here's a simple Markov decision process shown in panel B. One thing I find particularly interesting is that here there are two parameters, pi I and pi j, in the policy, and here you can see the trajectory during learning of those two parameters. They're converging towards similar directions, but you can see that the dotted line, which is using the natural gradient, is converging more directly. All right, so I'll end on this. So if you take a step back and look at all the things we said, the policy gradient theorem was really the starting point for much of what we did. And what we've seen is that there are different versions of this that all have the same policy gradient because the expectation over theta pi of all these quantities is the same. And so we can design algorithms using any of these things. And then the last one we saw is that we're going to use the natural actor-critic algorithm. Then in fact, the interesting thing is that this quantity is just W, the advantage function parameters. Okay, so that's what I wanted to say. And I hope there's time for what Katerina wanted to say. But while she's getting set up, any questions, comments? I really encourage you in this case to read those papers that are suggested on the second slide, because this stuff is kind of subtle, but obviously it's important. Yes?
Have you encountered any interesting applications
Of these methods. I think they're growing in popularity, actually. So the papers that I mentioned have some, but more recent papers, I think, rely more strongly on the notion of natural gradient. So it's still a kind of a research question of exactly when that can help and not. And in experiments people have reported, the outcomes are not unanimously in favor of natural gradient. But in the published ones, and of course that's a sample bias right there, they are. So I think it's still open. And so it would be an interesting dimension to explore in your projects, for example.
So if you're using the parameters that you for the Q as like your gradients for updating your policy parameters, how do you? That doesn't. I can't see how that like would converge to something because the parameters are probably not going to like be zero, right? So, or unless do the parameters eventually go to zero and then your policy is converged, or how does that work?
Say that?
I think it was really important that we had to like minimize the square error for the critic first before we can do anything.
Yeah, but would the parameters then be zero on your critic?
Right. But suppose you do let it converge, and then you freeze it and train the policy. It will tend toward the policy having parameters proportional to W. Now ask yourself this. If the log probabilities were set equal to the Q values, how bad would that be? What would be the most probable action? The one with the highest Q value. The short answer is I don't know the answer to your question. Maybe Katerina does.
So the log, yes. So actually, maximum entropy reinforcement learning, which hopefully we'll see on Wednesday, but it may be that we see it coming Monday, is exactly this. The log of the Q gives you the action. Okay? So we'll see a very strong connection between Q and actions, right? Mm-hmm. So maybe we'll revisit your question on Wednesday. Okay? We have 25 minutes. There are two important things I want to discuss. The first is the intro to the second. Asynchronous reinforcement learning, what can we do when we have multiple threads? And in the second part, I want that we discuss evolutionary methods. To understand what reinforcement learning is, it's good to see what it is not, okay? And contrast it on alternative, let's say, policy optimizations. I think this will allow us to understand better these policy gradients that we've seen so far. So we have already said that the fact that the data is non-stationary, okay, was a big problem, which for many years prevented researchers from training stable neural networks, right? Deep reinforcement learning. And we said that the big contribution of the 2013 paper from DeepMind was to introduce experience buffers, where the experience from the single-threaded agent who is exploring the environment, and yes, his sequential tuples are correlated, will all be thrown in this experience buffer, and they're going to be sampled. And the sampled mini batches from this experience buffer will be more stationary, right? Because some of them are going to concern this place, some they're concerned later where the agent went this way and this way, okay? And this will allow will stabilize training of, let's say, the Q function approximator, correct? And the problem, though, with this is that with using experience buffers is that you can only use off-policy methods, okay? Because tuples that are in the experience buffer were collected with older versions of the policy. On-policy methods require that the tuples you're going to use to take gradients have been collecting based on the current parameters of the policy, okay? That's why they're called on-policy. How can we do scalable on-policy learning? Here, this is the paper we'll discuss, asynchronous methods for deep reinforcement learning, which said instead of using experience buffer, let me parallelize the collection of experience across multiple threads on the same machine. Each thread is an agent, and they explore the environment in different parts, and they contribute their experience tuples all together to train a shared version of the network parameters theta. Does this make sense? And there were previous works. There was a paper called Gorilla, which had multiple agents which were in different machines, and this made communication harder. This paper proposes to put the different agents on different threads on the same machine, so communication is easier and is more scalable. All right? And we'll go into details of what each agent needs to communicate to the other agents for them to manage collectively to train a deep parallel algorithm. With what type of deep parallel algorithm this can be used? With any type you like. Both value function approximator, deep Q-learning, SARSA, as well as policy gradients. And in fact, the most successful, let's say, algorithm that resulted from this paper was what is called A3C, an advantage actor critic method, asynchronously trained in multiple threads on the same machine. Okay? Right, so another important point is the exploration. Because we have different threads, always the exploration will be better than epsilon greedy. Because different agents are in different parts of the environment. Okay? This is pretty straightforward. So let's see how an asynchronous version of deep Q-learning looks like. This is the pseudocode that runs on each agent in each thread. Okay? So remember, we have two versions of the network, theta and theta minus. Right? Because the one is the stable one that is updated periodically, and the other one is the one that we compute the targets from and is updated periodically, and the other is where we take the gradients. What does asynchronous update mean? This means that every agent collects experience, estimates its own gradient, and updates the shared version of neural parameters theta. Now, this theta parameter sits somewhere, and the agents send their updates, and there you can apply different locking protocols, like if I'm updating and you sending, maybe you should wait before I update, because if you don't wait, then you're going to see older versions of theta. So I think the different communication happened without locking, and it's still totally fine. Does this make sense? It's okay if once in a while one agent does not see the latest version of parameters theta. Okay? And the other thing that is good to keep in mind is that it's not that we take a step and then we send the gradient. We also accumulate information across multiple time steps. We estimate the gradient and then we send it. We try to minimize communication. If we communicate like extremely frequently, this may pose a problem. We're all the time going to be bumping on each other. Okay? Let's see if it's worth something here too. So this is the periodic update of the theta minus, right? Yes?
One quick question. You just mentioned that it would be fine if one of these working threads had an outdated theta, would they then make a wrong asynchronous update? Could you describe that better?
Yes, so they say in the paper that they didn't use locking, and it's okay. So basically, we are 8 threads, 8 agents, and there is a shared theta, and you send an update, and if this update is completely, has been completed before the other agent sends, then the other agent will indeed take the latest version of theta and move it to its own direction. If there is, without locking, potentially this new agent will override what the previous agent updated. Does it make sense? So even the simplest without lock type of communication, still it's fine. All right? Because in any case, these gradient substates are stochastic. It's not like they're golden. Okay? Okay, so this has been used quite a bit. And here is an actor-critic version. And why this is important? Because this is an on-policy method. Okay? So it is absolutely necessary to do multi-threading to have a reasonable speed-up. We have 2 types of gradients. One is for the value function, and one is for the policy. Exactly what we described in the previous sub-lecture. Here is the speedup. How is the speedup defined? The time required for a single thread to reach a reference score of the game. This is averaged across multiple games, divided by the time required by n threads. Ideally, the more threads, the higher the speedup, right? And the whole grail in those asynchronous methods is to show that you have very good, you scale very well, and the more threads you put, you see ideally linear, speed up, a linear, increase in performance, and usually this doesn't happen because at some point the communication between the agents becomes a bottleneck, okay? What do the agents communicate to each other? We'll see it in a few slides later, but could you tell me what do the agents communicate? Very long gradient vectors, right? Depending on how many parameters you have in your neural network, that many values you need to send, okay, to perform this gradient update. This is quite a bit of communication there. The buses are going to be pretty dense. Yes?
So, I mean, the advantage of this algorithm that you're describing is the fact that you can run your simulation on multiple threads, right?
Yes.
I don't know if they ran this on Atari, which is like a 40-year-old game system, and so you can run many instances of Atari. But I guess it's a trade-off between trying to communicate updates from the network and your thetas, right, versus the actual size of your simulator. Because if you've got a huge simulator, you can't just run it on 16 threads in one system, right?
Because they're expensive.
Because they're expensive. So maybe in that case, it would be cheaper to actually move the network back and forth. Move the thetas back and forth as well, right? Over a network, I suppose, using some shared memory or something on the thread.
1 second. So each one of them needs to have its own simulator, right? Which vary in different points, so that's for sure.
Right.
Okay? And each one has its own version of computes its own. They all share the theta, right? And they compute the various updates and they communicate to the central place, right? To update the network.
Right.
So I didn't understand what you said with the size of the simulator. Let's say we have a very heavy simulator.
Right, and so then you can't run 16 of them on any machine, right? In which case you don't talk about a shared memory structure where you put your theta.
Right.
Instead you use the network to transfer the
Okay,
theta.
great. So then the whole grail in industry right now is how do you train, let's say, deep learning models in multiple machines, and who's going to show the best scaling, like the more machines, the faster you train, okay? And yes, this is a very, very important, I suppose, point that you're making. So what you're saying is that if previous paper already showed that you can do it with multiple workers sitting on different machines, what is the big importance of this particular paper?
Especially if they're using something like Atari, which is, like, again, it's a 40-year-old machine, right? Like, basically Atari.
It's a very cheap simulator.
Yeah.
Right. So I would like to tell you that this has also been used right now in, for example, for robot farms. You have multiple robots. Again, each one is exploring different parts of the state space, in particular different objects in their bins. They compute gradients and they send their gradients in a global policy who is learning to grasp. So this has been done in Google with 15 different robots, okay? And sure, each one is completely independent. I totally agree. I don't think I know the details between within machine, cross-machine, bottlenecks. But my point here is that, yes, in real life, we have one agent who is exploring. When you go in simulation, you can totally parallelize your experience, okay? Parallelization real life is much harder, but it's still possible. Again, many people have taken this direction very seriously, and they try to coordinate between researchers in robotics so that whatever tuples I collect, maybe I can share them in the robotic cloud, and you can take those examples and also train your network. Yeah.
How should we interpret like the superlinear speed up in this case? Is it that if there's multiple threads, then they get closer to the optimum in the process they train faster also?
So we'll show some curves here of the time, right here. So the yellow curve is the one that has 16 threads, okay? And of course, it takes the slowest time to train. Now what you're saying is that, how do I interpret, let's say, superlinear versus...
Like it says more than 16 times faster for 16 threads or something.
Right, but it also doesn't get stuck enough because it's not just about how much data you get, but also what type of data you get. So they also get very diverse data. Does this make sense? So it's not easy to say, oh, I use 1 million frames, and then you use 2 million frames, so probably you're going to be twice as fast. It depends what types of frames you use. If you use way more diverse frames than me, you should be way, way faster. Does this make sense? So the diversity of the data counts, not the size of the data.
So like if we had a single thread simulator and it was like oscillating between two different parts of the environment. we also
But
get,
you cannot oscillate. How are you going to make it oscillate? Like kill it and it all the time dies and stuff?
like run two different simulators but only use one of them at a time.
Oh, I see. Yes, yes. This is good. Yep.
Okay.
Is urban explore definitely better than being stuck in the same place, right?
Okay, makes sense.
Yes, but it's a very good point. The diversity of the data is all that counts. Because many times people say, oh, but I have 100,000, actually this is 100,000 of little multiboxes, and they are all collected from the same ground that is running around on the same place, tracking the same bicycle. And they're always, the multiboxes are all about the same, let's say, bicycle. So the number of data is irrelevant, the diversity is what counts. Okay, so evolutionary methods. So far we've discussed, we have this following optimization problem, right? We're trying to find the parameters theta over policy to maximize the returns, okay? Imagine that Q0 is some initial state distribution, okay? What tells you which states are the initial states, and you try to maximize the returns from those states, okay? So that's what we're trying to solve. That's how we have motivated so far. And, well, reinforcement learning methods exploit the structure of the problem. They say, you know, this reward of a trajectory is a sequence of states, there is an agent that sequentially visits the states and updates rewards, and can I use this structure to try to optimize my objective better? And we'll see what I mean by structure by comparing to methods that do not exploit such structure. We have seen two sets of methods. On the left, or on your right, are methods that try to estimate value functions, state value functions or state action value functions. And essentially they're all about Bellman, applying the Bellman updates, right? And essentially are all versions of dynamic programming, okay? And on the left, we have methods that directly try to optimize the policy as is shown in this objective, okay? And then we saw also those actor-critic methods that are in the middle of these two sets of methods that both try to estimate the value function and use it to update the actor, which is the policy. Right? Do you like this categorization of methods? I think it's very clean, very nice. Now, all of those have broken those returns into time steps, or many of them at least, into time steps, and they try to take gradients. And what we're going to see in this lecture is that there are methods which, here we go, there are methods that just consider the following black box maximum. Here is the parameters of your policy network, and here's a black box, and here is the return, like how good is these parameters for your policy. And they don't explain anything else about the structure, that this return is comprised of different states that add up together, okay? It's just trying to search over parameters theta of your policy network so that they achieved the highest expected returns, okay? And now you're going to say, but I think in Monte Carlo sampling we did the same thing, right? Well, there we were keeping track of states. Here we forget about states. The only thing we think about here is the parameters of the policy network. Okay? So the general algorithm is extremely simple. First, we'll initialize a population of parameter vectors. What is the parameter vectors? This long vector, for example, of my neural network weights. You initialize it. So each one of these in the population is like a genotype. That's why they're called evolution, because they have connection with how natural evolution works. The second thing we'll do, we're going to do random perturbations in those parameter vectors, okay? Which is what mutations, this is what called mutations in biology. Then we will evaluate each perturbed parameter vector to see if we ended up in a better place than what we were before. Okay, so we will evaluate the fitness of that parameter vector. We will keep the perturbed vectors that have highest fitness, and this is called selection, and then we will repeat. And because, you know, this is the most biologically plausible algorithm, because it's a very important now to say that my algorithm is biologically plausible. Let's see a very simple version of this. Imagine that we have d-dimensional parameters of our policy network, okay? And we'll describe them with a Gaussian that has a mu, a mean, and some constant standard deviation, okay? So it's an isotropic Gaussian and it's fixed, the sigma is fixed. So the only thing we'll update is the mu. So first we'll initialize different mu's. So we'll sample different parameters from this mu. For each of those parameters, we will try to evaluate its fitness. How we'll do that? Each theta gives us a policy. To evaluate the fitness of the policy, we need to essentially sample rollouts, trajectories, and compute their returns. The return of each trajectory, either episodic or discounted and the truncate discounted. And then we'll keep the top k% of those parameters, and to those we will fit a new mu, and we'll update. Okay? I think here we also update the sigma. It's just this isotropic Gaussian, while in a little bit we'll see that it doesn't need to be an isotropic Gaussian. You can have a full covariance matrix. Okay? And there has been many algorithms in robotics that do exactly this, and they vary on how exactly they update this parameter mu, but most of them, they consider such Gaussians. They consider the parameter vector, which is represented this Gaussian policy, and you try to find the best parameters of this Gaussian, which if you sample, you will end up with good parameters for your policy. Now, the big confusing point here is the following. So far in the course, we've always have been talking about action distributions, okay? Distribution of our policy and actions that we're going to sample actions. Here, we're never going to talk about this. This distribution is a distribution of parameters, all right? So instead of having point estimates, we have a distribution, and if you sample, you instantiate a neural network, okay? So the sampling is in the parameter space. It's completely different. I mean, it's not completely different. In fact, that's the whole point of the lecture, that it is not completely different, that you have two sets of methods, policy gradients with sample actions and evolutionary methods with sample parameters, and, you know, try to see the similarity between them, okay? So this is the problem you try to solve. And so, because we don't have much time, another version is covariance. You don't need to have an isotropic Gaussian. You can also have a full covariance matrix. How does this work? Well, you sample against some parameter vectors, you evaluate them, You pick the top performing ones, you update the mean, and then you update also the covariance matrix, and you iterate. And this is called covariance matrix adaptation and has been used quite a bit in the graphics community to optimize their policies for making characters that move around, and these policies are usually very low dimensional, like 22 or 100 parameters, okay? And usually, whenever we talk about CMAS, covariance matrix adaptation evolutionary strategy, we use the word embarrassingly. It works embarrassingly well. Because if evolutionary methods work so well, then there is no reason to teach a reinforcement learning course. Does this make sense? We will just do black box optimization to estimate beautiful policies, okay? Does this make sense? Okay. And the good paper to read is this paper that essentially the abstract says that, look, CMAS so far has been so good in Tetris, all, how to say, attempts of dynamic programming have achieved much smaller scores than just CMAS, and for the first time, with some smart engineering of the features, we are able to do better using approximate dynamic programming. Okay? Now, what is the big question that is in your minds right now? It is the following: that since evolutionary methods have been used successfully to train low-dimensional policies, can we use them for high-dimensional policies? Policies that are neural networks, that are encoded from a neural network, okay? With thousands of parameters. Does this make sense? If I can do this, then why do I need to do actor critic? I'm just going to do a black box optimization. And we know that black box is important because the most generic is your optimization, the more people will do research on it, the more code will be available online, and is much easier, right, than being domain specific. So before going to this, so this is a big question, we will consider a very particular, how to say, evolutionary algorithm, set of evolutionary algorithms called natural evolutionary strategies. So they will consider a distribution of our policy parameters. We said that before, that now we're trying to estimate parameters for a neural network, so we consider a distribution of those, okay, which is parameters, for example, by a mean mu. It makes sense? So you have a mu, then you have some sigma, you can sample and you associate different policies. Does this make sense? Okay, so the question is, how do we shift this distribution mu? So don't get confused now because it's a distribution. If you are confused with this, just think of the mu, the mean, and you try to find the right neural network parameters, okay? It's just, this is the most general way to think about it, all right? Now we're trying to shift this distribution to do well and to maximize our objective. Let's see how to do it. Well, let's see. So, what is f of theta? Theta is some neural networks, some neural network of a policy, okay? Is the neural network weights of a policy network, and f of theta is how good is this policy, all right? This is the expected number of returns. You do a bunch of rollouts, you aggregate, and you say, okay, this is how good is this policy. Makes sense? And we need to take now a gradient with respect to mu of this expression. So, whatever we show here, we have seen this proof before, where when the distribution pi was not over neural network parameters, but over actions, okay? And it's exactly the same steps here. You want to take the gradient over mu, the gradient goes inside, you multiply and divide with this distribution over neural network weights this time. This can be written as a grad log, and now you have an expectation of this score function. So the gradient of the expectation is the expectation of this score function, okay? Same as before. So natural evolutionary strategies consider this gradient to update the parameters. And we will have a very concrete example right at the next slide. So imagine that this distribution over neural network weights is a Gaussian, okay? So I have some mu, it's how long is the mu, as many as my neural network weights, okay? And I have a covariance matrix sigma square I, it's isotropic. It doesn't matter. So let's take the log of the pi. Well, how it's going to be? Well, if you remember how the Gaussian distribution, the equation looks like, essentially the exponent goes away with the log, and this is what you end up with. Does this make sense? And then, if you take the gradient with respect to mu of this quantity, you end up with this. Isn't this very simple? So this makes lots of sense so far. Now, let's try to draw two different samples theta from that mu. Okay, we said that we're going to sample parameters, we're going to fit them, keep the best, and update. That's what we said. So let's sample two thetas, theta 1 and theta 2. And then, to evaluate those thetas, each one of them instantiates a policy network. I'm going to do a rollout. Do you think I should give up on trying to explain this because it's 122? Or, I don't know. Yeah, I don't know. I think it's really important, guys. Let me fast forward, but on Wednesday I would like to spend 5-10 minutes on this. Essentially, simply by replacing on the above identity, this is what I get. Okay? Where the theta is sampled from this pi, right? So now, how you sample? You did only 2 samples. Well, that's fine. Here you go. Okay? Now, the interesting thing is, how do we sample thetas? How would you sample the theta from the Gaussian mu? If I tell you, here's the mu, sample me 2 parameter vectors. How would you do it? Well, this is how we sample from Gaussians. We have the mu, you sample epsilon. This epsilon comes from a Gaussian which is zero-centered and has unit, yes. And then you do mu plus sigma epsilon 1 for theta 1, mu plus sigma epsilon 2 for theta 2. All right? Epsilon 2 is as long as your neural network weights. Make sense? Very nice. So now here is what happens. If you put this theta 1 there, the mu cancels, and this sigma cancels with the denominator. So what we are going to end up with is this. Okay? And here is the general algorithm. And here we're going to stop and we'll continue next time. You have a mu. You sample epsilon 1, epsilon 2, epsilon n, as many samples you want to generate. Okay? Then you get the theta plus sigma epsilon I. These are the new policy networks. You evaluate them using rollouts and trajectories. And then here's how you update the theta. So the interesting thing is that these natural evolutionary strategies have a smart way to update the theta, which does use this exactly the score function estimator that we have seen for policy gradients. Okay? So now the interesting question is, if both of them use the similar identities, what is the difference between sampling in actual space versus sampling in the parameter space, and which one of the two is better? Okay? So we'll see some results of this in the next lecture, and in the next lecture I hope that we'll get to excellent last year, I would say very, very recent, progress on stochastic policies and maximum entropy reinforcement learning methods that instead of just using the objective of maximizing returns, they also maximize the entropy of the policy. Essentially, they say maximize returns, but do not overcommit to a policy. If 2 policies give you the same returns, keep both of them. Okay, and we'll see how this results in very, very beautiful algorithms.